Good morning, everyone, and welcome to today's PHTV Policy Committee webinar. I'd like to thank Lauren Bortolotti and Lyle Boychuk for agreeing to do today's presentation, which will be on classifying Prairie Wetland Permanence, a remote sensing methodology. Lyle, whenever you're ready.
Good morning. Everyone can hear me? Ian?
Yeah, I
good?
can hear you just fine.
Okay, thank you. I will proceed. Thank you for the opportunity from Lauren and myself. I really appreciate the opportunity to present this work. Lauren and I have been working on this on and off over the last year, and really excited to showcase this work to the broader community. I'm going to dive right in. I'm just getting organized here. Just give me a sec. So just first a quick overview of what we want to present today, and the structure of the presentation. Primarily our work has been in Manitoba, our testing area, and we're leveraging the current wetland inventory in the CWI. So really our objectives today are to establish the appropriateness of the CWI, to characterize wetlands, the wetlands of agricultural Manitoba, provide really an overview of the S&K system as it pertains to our methodology and how we're incorporating it into remote sensing method and characterizing it with remote sensing and statistical methods, and present the broader methodology to characterize the wetland vegetation within these wetlands, and basically go through everything: our image selection criteria, our training validation, and the technical methods that we've developed and applied here, and then dive in a little bit deeper. I'll hand this off to Lauren to describe the statistical work where we've paired these two approaches to characterize permanence at the basin level, and have a little bit of a discussion in terms of what's required to scale this method to large geographies. Why model wetland permanence? Currently in the Canadian wetland classification in the CWI, there is no permanence, no ability in that model to assign permanence, given that it's really specifically a prairie thing. But there's a whole bunch of applications where wetland permanence information at the basin level is required, whether it be carbon sequestration modeling, nutrient modeling, hydrologic applications. Essentially, S&K permanence is a critical information piece that basically would drive models on this front. Obviously, this is the PHJV, the wildlife habitat piece in terms of suitability for various species. Obviously, that's a critical information piece. But really, what's driving us here is what's really motivated this at this point has been Manitoba water rights regulation that was brought into being over last year, specifically trying to being able, from a regulatory perspective, separate out class 1 and 2s from higher permanence class 3, 4, 5s. So really the first thing I want to take a look at is when we started thinking about this, Manitoba, a large part of agricultural Manitoba has been mapped to the CWI standard, and it really makes sense that we would try and leverage this data and evaluate what the potential the CWI has for policy applications. DU and MHHC has been actively mapping wetlands to the CWI model since 2012. Keeping in mind the high resolution approach has really been the standard that's been applied across Prairie Canada, and agricultural Manitoba. The data that exists follows that model as well. This is standardized data following a standardized interpretation guide, classification guide, established at a 0.2 hectare minimum mapping unit, and it all falls to the mandatory content of the CWI model. So, i.e., having the class, the system, soil, and impact codes for each feature. In most of the work that DU's done, we've mapped the drainage. I know MHAC's product has moved away from that from a cost perspective. But really, the accomplishments to date have been pretty impressive. 33,000 square kilometers, about 32% of the agricultural zone in Manitoba has been done. Here's the current status provided by MHHC. You can see the areas complete are aligned really pretty much driven by the NAWANT priority target areas, both DUs and from the PHJV perspective. And there is some, MHHC currently has some mapping in progress right now. I think that it will be ready to be added to the master CWI data set, the areas in orange. The challenge in Manitoba is that, a lot of their photography is older. You look at our inventory years, there was a lot of work done in 2012, 2015, and by DU and MHHC going forward. And it's all been from the Manitoba ortho refresh stereo models. And if you look at the distribution of the image dates, a lot of that has been developed on older imagery, circa 2007, 2009. So when we talk about scaling this or looking at using this product for regulatory approaches, the first question comes, what is the validity of that information given its vintage? Which I'll touch on that a little bit further down the road in my presentation. Really, I'm not an expert on Stewart and Cantrud, but there are some really key concepts within S&K that we're leveraging as underpinnings to this model. Essentially, the S&K system uses wetland community structure within the basin to characterize basin permanence. S&K is attempting to look at long-term conditions, right? Not just a single snapshot in time. Ideally, if you kind of look at it in its purest form, you're characterizing a basin based on open water phase, normal emergent phase, but also the drawdown phases. So, you're trying to characterize the sort of the long-term average of that basin rather than what you're seeing on the ground at that time. You have to consider that. In a regulatory setting, and it seems pretty standard across the Prairie provinces, there's 5 wetland types. Basically, determined by the assemblage of the wetland communities and the distribution of those communities within the basin, representing specific flood regimes. So, really, the veg indicators are an indicator of hydro period of the wetland, but not directly related one-to-one of wetland flood frequency. And really, the presence and distributions of these zones are really the primary factors that trigger the differentiation between basins from one class to the other. and really permanence is really for the broader wetland defined by the veg zone occupying the deepest portion of the basin. And so really this is what we're trying to exploit here with this methodology. The presence of these distinct vegetation communities are the opportunity from a remote sensing perspective to try and see if we can separate them out, separate the vegetation communities within basin, and potentially model statistically, do a predict permanence class. So, and so we are looking for long-term average conditions. I think ideally, when we're looking at trying to use a single image date, ultimately we're trying to, the ideal would be capturing the wetlands in a normal emergent phase, and try and capture mid-season high vigor of the current season's wetland vegetation growth, and try and eliminate any noise introduced by ponding from runoff in the spring. Just a standard distinction between the classes and the concept of the distribution of vegetation structure within the wetland, differentiating between the permanence classes. So our method as being presented today, ultimately we're, from a policy perspective, we're trying to separate 3, 4, 5s from class 1 and 2s. I did some initial testing when I started looking into this, looking at SAR data and trying to characterize hydro period from multi-temporal data. My initial testing wasn't really promising, so we've gone down this path of looking at a single epoch of spectral data, and basically trying to identify these wetland indicator communities with rapid eye and sentinel multispectral data. And really we wanted to determine if either of them is appropriate in terms of spatial and spectral resolution. Can we consistently classify these communities within wetland? But that would really only get us a part of the way. Ultimately, taking that data and then further developing additional statistical models on the backside to predict permanence class, which is Lauren's part of the work. Study areas, we've attempted to essentially, originally we started looking at some legacy IW or permanence data that was developed for the assessment sites. So we initially centered our project areas around 2 sites in Manitoba, in Shoal Lake and Killarney. We found out early on that the mapping, the definition of the wetland feature that was done in that data was quite different than the delineation techniques and characterization of the CWI. But a lot of that data was, I think, late 1990s, and we found some inconsistencies with the permanence classification on those basins. So we've had to move away from that. But essentially, that was really what motivated us to start with these two project areas. They are slightly different in terms of their wetland distributions. They're both parkland sites, but we're fairly confident that these are relatively representative of the conditions that we could anticipate across the broad areas that have been mapped by CWI. Just a high level to look at the wetland or the distribution of wetlands and the land uses. These two sites are different. Shoal Lake has a higher abundance of wetlands density, but more are skewed towards larger wetland features. Our assumption being that there'd be a higher proportion of class 3 and above in Shoal Lake. Shoal Lake, like broader agricultural Manitoba, is dominated by annual cultivation, interspersed with remnants of grassland and woodland. The Killarney site basically has significant lower wetland abundance, and the density is lower, but there's actually the mean wetland size is significantly smaller in the Killarney. And so we're assuming that we'd be a tendency towards more seasonal basins there. And same holds true as Shoal Lake. Killarney is dominated by annual cropland as well. But there is slightly more perennial cover in the Killarney site. Keeping in mind that we're looking at, S&K being applied to isolated pothole wetlands that are, I'm using air quotes here, natural, not impacted. Makes sense that we take a look at the distribution of wetland impacts. Really, both sites relative to other places that we've mapped in Prairie Canada, I would characterize as moderate drainage abundance. Looking at drainage densities, 1.5 kilometer, 3.2 kilometers per square kilometer, would fall in the moderate range compared to some of the sites where we've seen as high as 8 and 9 kilometers of drain per square kilometer. Shoal Lake has slightly lower drainage density and per unit area lower abundance of drainage. But even though these areas are impacted, there's no doubt about that, there's still a high proportion of non-fluvial intact wetlands that we can apply this classification to. And we are seeing a range of conditions in terms of impacts across the two sites too, which should be representative of what we see across the broader parkland in Manitoba. So now, kind of stepping into the guts of the work. As I indicated earlier, we really lacked truth and training data from a permanence classification. So we initiated a small field program. We did have a limited budget, and we had to maintain, ideally remote sensing people. We want as many, more samples is always better, but we are constrained by time and cost. So we initiated a field transect program very similar to what we've done in the past for validating CWI data. Where essentially we run transects along roadsides sampling various densities of wetlands, select the CWI wetlands that intersect an observation boundary, and essentially type those wetlands from the roadside to compile our sample. And we also, this is all done with mobile application, ArcGIS, our collector. So the folks in the field are typing each wetland, but also identifying whether or not it matches with the ground, whether it agrees, or if we've missed one, or if there's been mapping in the CWI that the wetland doesn't exist, to try and get a better feel, I guess, for the validity of using the CWI, even in the first place. Is it still a valid data set for, does it meet an accuracy criteria that allows us to scale up? Along the transects, the field folks also would delineate any wetlands that we omitted and type them as well. So just to really speak to give us our sample from a remote sensing perspective for validation of the models, but also to give us some numbers on the quality of the CWI data and whether it's still valid today. There's the Killarney site. essentially that's the sample that we have to work with in terms of training these models or validating the model. Just to speak a little bit, I guess, to the quality or the currency of the CWI, is it still relevant? Keep in mind there's a 0.2 hectare size minimum map unit, so theoretically anything below that hasn't been collected in the CWI. But along all of our transects, we sampled 389 basins that had observations. We were looking at 71.4% agreement at the basin level, 93.9% agreement at the area level. So that's pretty good. Commission is very, very low, so there's only a couple, a handful of wetlands along our transects that were collected that aren't visible on the ground. But there is still high emission. We're essentially omitting just under 6% of the wetland area that we observed on the ground, and 22% of the basins. So again, I think the minimum map unit might be influencing this. So looking at table 2, the other thing we wanted to look at is what are the classes of the wetlands that we're sampling and that's being captured in the CWI, and from a general feeling, is it representative of what we would expect? Not surprisingly, class 1s are there's very few of them, only 3% of the basin. Class 2s approximately 30%. But then you could see, as expected, really high proportion of class 3 wetlands along our sample. And I think this is pretty much representative. There's really no surprises here. The other thing we wanted to look at as well, if you look at table 3, from the wetlands that we missed, that were omitted, what is the permanence class of what we omitted? Are we primarily omitting 1s and 2s, or are there higher permanence classes in those as well? The vast majority, just under 60%, are 1s and 2s, but along our sample, 38% of what we omitted are class 3s. So, I think the CWI data from an area perspective is still relevant. It characterized the distribution of wetlands really well, but we are missing some class 3s for sure. So this is sort of a first step before we proceeded any further. Looking at these numbers, we decided that it makes sense to move forward with the method. And run with the CWI data as our wetland mask. The other part of this is training the classifier to separate out the wetland vegetation communities in conjunction with our roadside transects, primarily on Crown and DU properties, and some where we had opportunities along the road. The field crews were sent in to characterize, to get pure samples, basically assuming a 10-meter buffer of low prairie, wet meadow, shallow marsh, open water, and deep marsh zones within these wetlands. And this is pretty time-consuming stuff. Our sample's pretty small from a training perspective. We only had 250 after our days of field. So we did do some supplemental work with air photo as well and added another 50, primarily in the open water areas, just to make our training a little more robust. So now kind of moving into the platforms that we evaluated and tested. really what we're trying to get at here is we wanted, we wanted potentially having a lot of imagery content available for us to exploit. I mean, we're dealing with optical imagery, cloud, you have to have a lot of collects in order to get a appropriately timed image in midsummer that's cloud free. So repeat frequency is important. Rapid Eye is chosen primarily on that basis that there's a revisit time of 5.5 days. We have pretty decent spatial resolution of 5 meters, and spectral resolution, the 5 bands are pretty good. And we have had some success in the past with water mapping and flood mapping using Rapid Eye, and the red edge and near infrared band have really performed well in terms of separating out flooded vegetation. So that's one of the reasons that we chose this, but there's also a lot of content. Rapid Eye is a constellation that's constantly collecting, and there's a lot of it's used a lot in Prairie Canada for precision agricultural applications. So when we start thinking that if we have a successful method that we want to scale and we need to cover large areas, Rapid Eye is likely a good candidate from that perspective as well. I guess I might add too, there is a cost associated with Rapid Eye. It is a commercial platform owned by Planet, but really from a image perspective, it's relatively low cost when you start looking at high resolution platforms. The other one we looked at, the ESA's Sentinel-2, which is free. You're sacrificing spatial resolution, where you have a mix of 10, 20, and 60 meter bands, but you're dramatically increasing your spectral resolution. There's 4 visible bands, number of bands within the near infrared, as well as some SWIR bands as well. Again, it has a high revisit time of 5 days. There's a lot of content available through the ESA, the Copernicus program, and so it seemed like a good candidate from that perspective as well. But the cost of free made it really attractive as a platform to test. In terms of really, I kind of alluded to earlier that we wanted to try and capture midsummer imagery in a year that is sort of trying to capture normal emergent conditions on the ground, and didn't want to, when the wetland vegetation is in high vigor. And I mean, ideally, where you would have multiple years for the basins to some climatic stability, I guess, is what I'm getting to. So when we look at 2016, looking at AEFC's drought watch product, in the previous year, the conditions are. In 2016 summer, are for the previous year, it's normal to slightly above normal. If we look over multiple years, over 2 years, again, our study area is normal to slightly above normal accumulations, and if we go back over 3 years, it's similar. So mid 2016 seemed like a really good year. We have a lot of midsummer imagery in both platforms available if we wanted to scale, and we're looking at yeah, I would, from a lot of what we've looked at with photography, we're looking at really capturing normal emergent phase, which I think is optimal for this application. There's the image dates that we managed to use for our testing. You know, essentially all mid-August, with the exception of the one rapid eye image that's early July. But that's basically the imagery sources that we interrogated. So in terms of starting to interrogate this and drilling down a little bit deeper, first thing we did was to take our field observations of wetland communities and see in each image source whether or not we can reliably separate out these communities spectrally with the imagery. The rapid eye data, actually pretty decent separability of our target classes. You can see we have, you know, quite a bit of confusion between the low prairie and wet meadow, which is not surprising that, you know, they're confused in the field as well. But we're able to separate out the other classes from the imagery pretty well. Especially in the red edge and near infrared band, they appear to be pretty darn important, and more confusion in the blue and red as well. But this was promising when we first looked at the separability. I was feeling pretty good that we could separate these communities, the structure within basin out. Sentinel, a little bit different, in spite of the lower resolution, still really good separability of our target classes. Again, there's confusion between the low prairie and wet meadow, but we have high separability in band 7 red edge, near infrared, the other red edge band, and the SWIR band. So it's basically suggesting that both of these platforms should perform well. What does the process look like? Basically, taking both the optical sources and through Send2 Core, which is ESA's standalone atmospheric correction program. We processed all the Sentinel imagery with that. We used AtCore and PCI to do the atmospheric correction and cloud masking from the rapid eye data, and we had a bunch of SAR data that was similarly timed that was used in my early testing. And we basically did the radiometric correction on that and terrain correction in SNAP. The workflow basically carries on from there, where we take the bands that performed really well, plus a principal component, just a PCI 1 of all of our bands that performed well from a separability perspective, in each of the platforms, and then stack them into specific image stacks that we've tested. The first one being primarily Sentinel. You can see the bands that we incorporated, the rapid eye data, and then kind of had a flyer there where we fused optical and SAR data. Basically all bands, the red edge, the Sentinel bands that we use, plus VV and VH from Sentinel-1. So the idea is we had 3 image stacks that were all downscaled to the lowest resolution as part of the process, and then brought in our field observations, and using random forest, the classifier, trained it, masked it with the CWI wetland data. So essentially just the classification internal to the basin, and generated wetland cover from the rapid eye, the Sentinel, and the optical stack, and then I provided those to Lauren, basically percentages of low prairie, wet meadow, shallow marsh, etc., for each wetland with a unique ID in the CWI for statistical processing to predict permanence. To give you an idea what it looks like, just conceptually, I guess, to give you an idea of what was done. There's the RapidEye data, the wetland cover mask that was aggregated by CWI Basin and provided to Lauren for statistical work. Same holds true with the Sentinel data, the 10 meter. That's what that classification looks like. And then the optical SAR comet stack, where we basically classified that as well. With that, I'm going to hand it over to Lauren and to describe the statistical work that she's done.
Thank you, Lyle. Ian, do you think you could confirm that you can hear me, see my screen, and let me know if you can actually see my mouse moving?
I can hear you, and it's loading. You're up.
Okay. Great. Thanks for that introduction. Before I jump into the statistical methods, I just want to first acknowledge the contributions of Llewellyn Armstrong, our statistician extraordinaire at Ducks Unlimited. So Lyle and I are presenting on this, but her help was absolutely invaluable in this. So my role in this was essentially to take the large amount of information that you just heard about from Lyle and create a statistical model to predict Stewart and Cantrud wetland class. To do this, we use classification trees. So it's a form of recursive partitioning where you split your categorical data into like groupings. And these models included 6 variables. So the first 2 variables, wetland area and perimeter to area ratio, come just from the CWI information. And then the rest of the cover variables, so percent open water, deep marsh, shallow marsh, and low prairie and wet meadow, come from the remote sensing that Lyle just told you about. And we combined the low prairie and wet meadow into a single variable, both because there was poor spectral separability in that RapidEye product, but also because we know that that wet meadow community tends to be a little bit sensitive to disturbance, and thought that it might not be a great indicator, especially depending on surrounding land use. We had between 376 and 378 wetlands to go into these models. Ideally, we would have been able to have a large enough sample size to split the data into a training data set to generate a model and a validation data set. But because we had envisioned this proceeding differently, as Lyle said, we had originally imagined using the assessment data more heavily, didn't quite have enough observations to do that. So used our entire data set for the model generation. As Lyle mentioned, there was 3 sets of imagery used, the RapidEye, the Sentinel, and then this stacked product, this combination product. And we used 4 different ways of classifying wetlands or grouping the wetlands. So Stewart and Cantrud, of course, we've got 5 separate classes, but what the Manitoba regulations actually want is just to find that breakpoint between classes 1s and 2s and 3 to 5s, which is essentially a 2-class system. And with the idea that depending on how you lumped or split these wetland classes, you could get better or worse model performance, we tried a variety of groupings. And with 3 sets of imagery and 4 groupings, when you look at all the possible combinations, you're going to have 12 models. And we need a way to identify, a best model or some better models. So that's a 2-step process. The first threshold that models had to clear was a threshold of having a Cohen's kappa greater than 0.4. And what Cohen's kappa measures is whether or not your model is predicting better than by chance. So obviously we want to do better than blind guessing. All the models pass that threshold. And so what we used instead was producer and user accuracy. That's what we're going to rank these models based on. So producer accuracy is the percentage of wetlands that have been correctly classified, and it's equivalent to 100% minus omission error. User accuracy is the percent of classified wetlands that are correct and is equivalent to 100% minus commission error. And I think an easier way to think about this is this somewhat silly example of this hypothetical landscape. So the top panel is what actually exists. And then the bottom panel, imagine it's a map that you've generated from model predictions. So in this example, the yellow features have very high producer accuracy. 1 out of 1 feature has been correctly predicted by the model. However, user accuracy is quite low, because if you were to use that bottom map and you wanted to visit a yellow cloud, only in 1 of 3 instances would you actually arrive at the feature you wanted to see. With the pink clouds, we've got the opposite situation, high user accuracy, low producer accuracy, and there does tend to be a trade-off in these 2 metrics. If we translate this to wetland classification terms, imagine that the yellow clouds are class 4 wetlands. Well, high producer accuracy is good because it's going to correctly protect features that merit protection under the regulations. But we've got an issue, and that's that, I don't know if you can see my mouse, but these yellow features that have been predicted to be class 4 but are actually, say, a class 1 present the opportunity for disagreement or conflict in a regulatory setting, where if somebody were to want to drain this feature, and in theory it's not protected under the legislation, but you've got this classification product that says differently, you've got the potential for friction. So we want to really minimize that, and so our goal was to choose a model that had as high user accuracy as possible to minimize those conflicts, but while still providing an acceptable level of producer accuracy. This table shows you the user and producer accuracy for some of the top models, as well as the best models from the rapid eye imagery, which are not immediately ranked below those others. The way to read this is the model name is the imagery that the variables come from, so Sentinel, Stacked, or Rapid Eye, and then 2C refers to the 2-class system, so matching the policy of separating out 1 and 2s from 3s to 5. What you can see is that we got almost remarkably high user accuracy levels, 92%. We were really pleased with that, while still maintaining acceptably high levels of producer accuracy. This table also shows you the 95% confidence interval, so that gives you some idea of the uncertainty around these accuracy estimates. And what you'll see is that the confidence limits overlap even among the top model and much lower ranked models. So for example, that Rapid Eye, that upper confidence limit, 90.9, falls within the bounds of the confidence limits for the top model. And what that's telling us is that ultimately, from an accuracy perspective, these models are statistically indistinguishable. Now, with larger sample size, it's possible that those confidence limits would shrink and there would be more separation. But what this means is that we can consider other factors other than just accuracy in selecting a best model. And very conveniently for us, that top model, that Sentinel 2-class model, has high accuracy, but on top of that, the Sentinel imagery is free, so we've got a way to keep costs down. And the 2-class system is just intuitive because it matches the policy framework. Now, despite these high accuracy levels, I think it's interesting to delve into where the model does not perform well. So what you see here is something called a confusion matrix. It is an output from the classification trees, and what you're seeing here is the confusion matrix for the Sentinel 2-class model. And the way you read it is in the columns, in classes 3 to 5, 216 of those features have been correctly predicted, and 35 have been predicted incorrectly, and so they're sort of under-predicted. The model thinks that they're in fact class 1 or 2, and then on the flip side, classes 1 and 2, 108 were correctly predicted, and 18 have been incorrectly predicted. Again, it's those 18 that we're a little bit concerned about because that's where we see the potential for disagreement, And so if we delve into the details of those specific wetlands, what we see is that the model tends to misclassify when you've got a class 2 wetland that is larger than average. So for example, there's a wetland in there that is over 10 hectares in size, and that's larger even than your average class 3 or 4 wetland. So probably not surprising that the model can't correctly classify it. And we've also got sites that have more deep marsh vegetation than expected. And this could be for one of two reasons. So number one, the deep marsh cover variable comes from the spectral classification, and there's always possibilities for errors and misinterpretation. There's still some statistics in that whole process. So maybe there is no deep marsh vegetation. Maybe we're just getting the wrong signal from the spectral data. The other option is that the Stewart and Cantor system is based on the vegetation that occurs in the deepest part of the wetland and assumes that there are these perfect concentric rings of vegetation around it. However, in real life, wetlands do not always look that way, and it's possible that what you have is a class 2 wetland with some adjacent patch of cattail, especially in Manitoba where we've got hybrid cattail. That's totally possible, and so that's where the deep marsh signal is coming in. Again, I think it's pretty understandable that occasionally the model is going to misclassify, and the nature of these errors don't worry me too much because they're understandable. I'd also be interested in seeing what those errors look like in terms of wetland area. So those 35 wetlands that were misclassified as 1s and 2s are equivalent to about 16.5 hectares. Whereas those 18, because we're dealing with larger than average class 2s, actually account for 28 hectares. So we get a little bit different information depending on whether or not we're looking at basin counts or total basin area. Now, we've got a statistical model that we think performs really well on this data set from Killarney and Shoal Lake, which do represent somewhat of a gradient of Western Manitoba. But of course, the next question is, if this is going to be useful in almost any context, well, we need to scale it up. And the first question we have to ask is, can our model represent the broader area? So the image is again sort of the area of CWI we have in southwest agricultural Manitoba. Our model had 377 basins representing 932 hectares, but Western Manitoba contains 289,000 hectares of wetlands. So that's a pretty big leap. We're probably not ready to say that yes, our model is totally representative of that. So Lyle and I decided to go for sort of a mini scaling up. We took the training data, so 932 hectares, and went to an intermediate scale. So we're taking a model generated from 377 basins and applying it to 28,000 basins. Sort of in the Killarney, Shoal Lake areas. So Lyle basically had to process a lot more imagery, provide me those variables, and then I applied the statistical model to this new data set. And just as a little check, in our original data, 67% of the basins were class 3 to 5, and they accounted for 92% of the total area. And in this new area, we saw that 54% of the basins were class 3 to 5 and represented 87% of the total area. After I run the statistical model, I then provide the classifications back to Lyle, and he can produce these really fantastic maps that look like this. So on the left, you see the classifications for Killarney. On the right, Shoal Lake. It really helps you visualize how the landscapes are indeed a little bit different. And what you'll see is the red features are the class 1s and 2s, and the blue features are class 3 to 5. And I think this is a great product because it's intuitive, it's simple, it's straightforward, it has the potential to be hugely time-saving in a regulatory context, and it's backed by what we think is a pretty robust process. Now, obviously, we have more work to do. There's a huge amount of work on Lyle's end in processing, new imagery and generating new variables. And very importantly, we do hope to expand our field program to get data in new landscapes in Manitoba and incorporate those into the statistical model. And what we would expect is that probably our accuracy is actually going to drop when we try and incorporate new and different landscapes, but we will have greater confidence in the ability to generalize reasonably across all of southwest Manitoba if we do this. So ultimately, policy was the motivation for getting this project going, but there are other applications. I see huge value in wetland permanence information, in modeling of ecosystem services from wetlands, in wildlife habitat modeling applications. And the statistical models are actually quite flexible in that if the breakpoint you're interested in isn't 1s and 2s versus 3 to 5s, you can quite easily tweak the statistical model. It's got a lot of flexibility. And again, right now it's just focused on southwest Manitoba, but with a little bit of effort has, I think, potential to provide us a valuable piece of information about wetland basins for a variety of applications. So thank you very much for attending the webinar, and I think we do have a little bit of time for questions.
Thank you, Lyle and Lauren. If you have a question, please type it into the chat box, and I'll Okay, the first question is, if a 10-hectare Class 2 wetland has a 1-hectare Class 4 area, how would the total area be rated?
I'll take that one. Essentially, the deepest portion of the basin, it should be basically classed as a Class 4.
Okay, so the entire wetland area would be considered Class 4, Lyle?
Yes. We're basically in the model. We're basically classifying the entire basin, not the hydro period of the structures or the communities within the basin. It's the entire wetland.
Right, one classification per basin.
NAR seem to have the highest separation. Could you just use that?
Yeah, you could, but the decision tree within random forest, if a band is little consequence, in terms of correctly identifying or making that split between classes, its influence is minimized. So there's really no, I don't think there's any advantage to distilling it down even further. But yes, the NIR band is important. The SWIR band actually is as well.
Okay. I don't know if you can see the comments, but Jim, very cool.
Thanks, Jim.
Thanks, Jim.
Okay. What Jim said. Thanks for the webinar. All this is useful work. That was from Mike Anderson. Since there appears to be no additional questions, I'd like to again thank Lyle and Lauren for their presentation today, and I hope everybody joins us next month for our next PHJV webinar. If you have any additional questions, feel free to send them to myself or Hugh, and we can get them to Lyle or Lauren. Again, thank you for attending today's webinar.
Thanks, Ian. Thanks, everybody.
Yep, thank you for the opportunity.